codes. So in the next slide, so hope both the sections are in the next slide, right? Cyclic codes.
Hello, sir.
Yes.
Sir, I will off my mic, please.
Yes. Okay.
1 minute.
Yeah, now here we are seeing the second slide, that is cyclic codes. So these cyclic codes are again a subset of linear codes. Earlier we have studied about linear block codes. This belongs to the same family of linear codes because it exhibits the linear property. If you see the second line there, V is equal to V1, V2, V3 up to Vn minus 1. It's a structure of code word of a cyclic code. So V1, V2, V3, Vn minus 1, what are they? They are different bits, maybe zeros or ones. In general, I have mentioned it as V1, V2, V3 up to Vn minus 1. And this V exhibits the cyclic shift property. What's the meaning of cyclic shift property? In case of cyclic shift property, we will be shifting these bits, for example, V1, V2, V3, Vn minus 1, to the right by 1 or 2 or any number of positions in a cyclic manner. So when we shift it to the right, what happens? V1 goes to the position of V2. V2 goes to the position of V3. In the same way, the last bit, Vn minus 1, takes a cycle. So it comes to the first bit position. Can you see there? Yes. So in the third line, it is mentioned that now the cyclic shift of V, which is basically a time shift by 1, will look like V1, that is equal to Vn minus 1, V1, V2, V3, and Vn minus 2. That means basically we are shifting it to the right by 1 position. Similarly, shifted by two positions, how it would look like? That means you need to shift again by 1 more position to the right. So the last bit was Vn minus 2, that will come to the first position. That means it will take a cycle. And Vn minus 1, which was at the beginning, that moves to the second position. And V1 will move to the third position. V2 will move to the fourth position, and so on. So this is again shifting by 1 more bit position, Vn minus 2, and so on. So that is V2. So initially we had V, we shifted it by 1 position, we called it as V1, and again we shifted it to the right by 1 more position, and now it is called as V2. So similarly, we can keep shifting it V3, V4. That means we'll be shifting by so many number of bit positions. So when we shift it, what happens? That we will see in the next slide. Okay, here in this slide, a linear code is said to be a cyclic code if the cyclic shift of each code word is a code word. So what's the meaning here? We have shifted, right? Initially we had V is equal to V1, V2, V3, and so on. We shifted it by 1 position and we called it as V1. V1 is a 1 bit shifted version of V. Next we shifted again, V2. It's a 2 bit shifted position of V, right? So you shift any number of bits, no problem. Maybe V1 or V2 and so on. So every new shifted bit sequence is a code word in the original set of code words. That means initially you had a set of code words in V, you shifted it by 1 position or 2 position and so on, any number of positions, and you got a new sequence, right? V1 or V2 and so on. So all these new sequences which are resulted due to the shifting are again a code word that belongs to the original set of code words in V. That's a linear property here. That is a cyclic shift. Even after the cyclical shift, what you get, that's again a code word which belongs to the original set. Somewhere you can map to the original set. Then it's a linear code. Or specifically here, it's a linear cyclic code because we are cyclically shifting. We are rotating. The last bit will becomes the first bit, right? Cyclic, a circle, that kind of rotation we are doing or shifting we are doing here. So that is the linear property or cyclic linear property. So even if you shift, a newly generated code can be mapped to the original code, or it is in the set of original codes. Okay, so we will express it in a different way. We see here, we shall write v is equal to v1, v2, v3, vn minus 1, that as a polynomial. How to write it as a polynomial? That is, we are associating some x, some polynomial with it. So that we write it as v of x is equal to v1 plus v2x plus v3 multiply x square plus v4 multiplied by x cube and so on, vn minus 1 multiplied by xn minus 1. So what is that? Initially we had a bit sequence v1, v2, v3. Now we are associating some polynomial with it, like an algebraic expression we want to represent it as. So what happens? We multiplied by x powers. So v1 multiplied by x power 0. So that is v1 itself. Plus v2 multiplied by x power 1. v3 x multiplied by x power 2. Next, v4 multiplied by x power 3 and so on. We just increase the power of x by 1 as we move on to the different bits v1, v2, v3 and so on. So these coefficients are 0 or 1. So these values of the coefficients are 0 or 1 because we are talking with about binary here. Okay, so we will move on to the next slide to see more details. Okay, so in the previous slides I just mentioned what is a cyclic code. So basically cyclic code is a family of linear codes, because in the previous lectures we had talked about linear block codes. So this is also a linear code because it exhibits a linear property. How it exhibits a linear property? Because even if we shift the codes, original codes, in a circular manner towards the right and circular manner, the newly formed code words still belong to the original set of code words. So that's a linear cyclic property. Okay, what benefit we have with the linear cyclic property, cyclic codes? So cyclic codes have well-defined mathematical structure. So this can be easily represented in the algebraic form, the polynomial form that we saw previously. That's a benefit, and also it has some other mathematical structures. So since we have some mathematical structure, it is easy to prove or unprove certain cases. It is easy to apply to the communication engineering field because mathematics everyone knows, and it's easy to deal with mathematics. And also we can have a structure if we have a mathematical framework. Okay, second, the design of encoder and syndrome calculator circuit for the cyclic code is simple. So simplicity with the encoder design and syndrome calculation, because there is no much matrix multiplications involved here. They are just implemented here with the help of shift registers. So we are avoiding some complex matrix multiplication, which was there in the case of linear block codes. We are avoiding that. We are just simplifying that with the help of some shift registers. Third point here is cyclic codes also detect burst errors. In case of linear block codes, if you see, we saw all the examples that could only detect a single bit errors. If there is one error, it can detect. If there are more errors, then it cannot detect. So burst error represents a sequence of errors. For example, if you transmit 10 bits, bit number 4, 5, 6, 7, all are having errors. That is called as a burst error. At some point, a continuous sequence of errors is called as a burst error. So this can detect, cyclic codes can detect that. Fourth point here is code words and syndromes can be generated by using algebraic expression. This is similar to the first point I mentioned. We can represent it mathematically. Mathematically in the sense, mainly algebraic expressions we can give to these code words, like multiplying by x, x square, x cube, and so on. It becomes much simpler to represent. Okay, so these are the advantages. In the next slide, we see the disadvantages. Yes, here we have the disadvantages. The error detection in cyclic code is simpler, but error corrections are complicated. Yeah, it can detect burst errors, but correcting is a little problem. Why it's problematic? Because of the combination logic involved. Why do we use combination logic? Because we'll be using shift register to shift the shift in a cyclic manner. So that's why it is a little complicated with respect to the detection part. Sorry, correction part, but the detection part is much easier. That is one of the advantage. It can detect the burst errors. That is an advantage, but correcting the errors is a problem because of the combinational circuit involved. Yeah, these are the advantages and disadvantages. In the next slide, yeah, now I think you should have a pen and paper, or just I think you know this maths, but still, but this is important. This fundamental mathematics is important for many cases. In today's lecture, it's important. Also, in the future, maybe some courses like internet engineering, or what you call here in VTU is computer communication networks. Yeah, we deal with these error control techniques. So this math is important for that. Okay, uh, we'll see some simple math here. So the first line here, g1 of x, is represented by an algebraic expression, that is x cube plus x plus 1. g2 of x, that is represented as x cube plus x square plus 1. Now we want to multiply g1 of x multiply g2 of x. Do you know how to do this maths? This is similar to the algebraic multiplication, but here the sum plus is XOR operation. Okay, so how to find this g1 of x multiply g2 of x? If you have a pen and paper, you may try by yourself. So first here is the first term of g1 of x, you are multiplying with the first term of g2 of x, and second term of g2 of x, and third term of g2 of x. Then second term of g1 of x, you are multiplying to all the terms in g2 of x. Next, third term, that is 1 in g1 of x, you are multiplying with x2, sorry, x3, x2, and x1. So this is a same math, but if you try it, it becomes more perfect. Okay, so first x3 multiply x3, that is x power 6. Next, x3 multiply x2, x power 5. Next, x3 multiply 1, that is x3, plus x multiply by x3, that is x power 4. X multiply x square, x, that is x cube. X multiply 1 is x. Finally, 1 multiply x3 plus 1 multiply x2 plus 1 multiply 1. And then you add up everything. So when you add up everything, you can notice that there is x cube plus x cube plus x cube, right? So this plus here is XOR operation. So x cube plus x cube is what? It is 0, right? Because a XOR a is 0. So x cube plus plus in the sense XOR or mod 2 of addition, x cube plus x cube is 0, plus x cube is what? X cube, right? Yeah. I mean, you need to be careful regarding addition. Addition is here indicates a mod 2 addition or logical addition. So you cannot write x cube plus x cube plus x cube is equal to 3x cube. You cannot write that way. X cube is basically a logical operator. That is, I mean, logical number, maybe 0 or 1. So in that way, you need to think. Okay, so when you sum up all those things, you should be getting the result as indicated there in the last line, x power 6, x power 5, plus x power 4, plus x cube. Why there is x cube? Because in the line just above the final line, you have 3 x cubes there. You have to add 3 x cubes. So x cube plus x cube plus x cube. So that gives you 0 plus x cube, that is x cube itself. Because 0 x or anything is equal to that anything. For instance, 0 XOR 0 is 0, 0 XOR 1 is 1, right? Yeah. So this is the simple math. I just went through it. And next one, in the next slide, yeah. Can you solve this? This is a division operation here. We have x power 6. I want everyone to try this by yourself. X power 6 plus x power 5 plus x power 4 plus x cube divided by x cube plus x plus 1. How to solve this? So it's like a reverse operation of multiplication, right? So when you divide x power 6 by x power 3 plus x plus 1, you have to check how many times x cube will be there in x power 6. You know this operation, x power a multiply x power b is equal to x power a plus b, right? That identity you should know. Okay, you click again, slide. Yeah, here I have just pasted the solution. Uh, I cannot open the pointer, so I cannot explain you. It's fine. Okay. So here on the leftmost corner, we have x cube plus x plus 1, right? That we have to divide x power 6, x power 5, x power 4, and x cube. And on the right side, first line right side, you have some one bracket and some content, right? That is the result of division. Uh, yeah, I just wanted to explain you with the help of my pointer, but I do not have access to anything. I'm like handicapped here. So I'll just explain this to you. Otherwise, maybe I'll take up this in another session. So here, basically what we do, we have to divide x power 6, x power 5, x power 4 plus x cube divided by x cube plus x plus 1. So first we check x cube, how many times is in x power 6? That is x cube times, right? X cube multiply x cube is equal to x power 6. And x cube, that's the first term on the right hand side, x cube. And you are multiplying that x cube, yeah, you are multiplying that x cube to all those terms, and you get the second line, x power 6 plus x power 4, second line, plus x power 3, right? So that is how. First you are multiplying x cube to all the three terms, basically x cube multiplied by x cube plus x plus 1. So you get x power 6 plus x power 4 plus x cube. Okay, then you do the subtraction. Third line, you have the subtraction, x power 5, right? Why it's x power 5? You see the two lines we are subtracting. X power 6 and x power 6 will cancel. X power 4 and x power will cancel. X power 3 and x power 3 will cancel. I mean, when you subtract. Only what is left is x power 5. That is in the third line. Okay. Next, you need to continue your division, right? So you need to take the two more terms from the top. This is how you do the general division. The same technique. Okay, so you get that in the fourth line, you get x power 5 plus x power 3 plus x power 2. Okay. Now you have to divide that by x cube plus x plus 1. So how many times x cube is in x power 5? You need to check. So that is x power 2 times, right? So that's why the second term on the right hand side of the first line, you see, is x square. Okay, so what you are doing is x square multiply by x cube plus x plus 1. So your fourth line, you have x power 5 plus x cube plus x square. Okay, in the fifth line, again, you have to minus. So x power 5 will cancel. You are left with x power 3 plus x power 2 in the fifth line. Okay, then you have to continue again. Some terms from the top, you need to take it down and continue, right? So we have x cube plus x plus 1. That comes down. Okay, then you have to check how many times x cube is present in x cube. That is 1 time. So in the first line on the right hand side, the last term is 1. Now you have to multiply 1 by x cube plus x plus 1. So you have the sixth line as x cube plus x plus 1. And again you minus. So you get x square plus x plus 1. That is a remainder. Okay, so I'm sorry I could not go through it as I wanted to do. Okay, so maybe if you have questions, I will take up maybe in the next session, or I will try to give some supporting material to this. So this is actually, the operation is similar to the general division operation, but you need to be careful regarding addition or subtractions. Okay, so what is the answer finally? The remainder is x square plus x plus 1. So this is how we do the division operation. Okay, let us move on to the next slide and see. Okay, now you will see an example. So those basic mathematics, what we saw in the previous two slides, that is multiplication as well as division, that we will be using in these examples. Maybe in this example or the examples I have later on, we will be using that same idea. Okay, we will see the one example here. Show that the code, there are 4 codes given: 0000, 1010, 1111, 0101 is a linear cyclic code. So we have studied how to show it is a linear cyclic code. Basically, what is it should exhibit the linear and cyclic property, right? So how to do that? You know what is the cyclic property? I mean, basically you need to shift the given sequence, and when you shift, you get a new sequence. Can this be mapped to the original set? Then it's a linear code. Okay, we will see that. We just need to verify that. So we know in the question that there are 4 codes given. First code is 0000, second code is 1010, third one is all ones, fourth code is 0101. So we call them as V1, V2, V3, V4. Okay, now we need to add 2 things. Any 2 things. We can add V1 with V2, or V2 with V3, V3 with V4, or V1 with V2, anything you can do. Okay, since I have not shown here V1 added with anything, because you know what happens when 0 is added with anything. Add, when I say add, this is XOR operation. 0 XOR X is what? X, right? So it's very simple. So I have not shown, but you can verify that. Okay, now let us consider V2 plus V3. What happens? What's the result of V2 and V3? So when we add V2 and V3, we will be bit by bit XORing. That is the first bit of V2 and first bit of V3. 1 and 1. What is the result? 0. Yes. Second bit of V2, second bit of V3. 0 and 1. It's 1, right? Third bit of V2 and third bit of V3. 1 and 1 is 0, right? Next, fourth bit of V2 and fourth bit of V3. 0 and 1 is 1, right? So V2 plus V3 is 0, 1, 0, 1. What is 0, 1, 0, 1? In the given question, 0, 1, 0, 1 is equal to V4, right? So addition of 2 code words resulted in something that is in the original set itself. Yes, very good. Now also we see V4 plus V2. What happens when you add V4 and V2? Yeah, the same operation. Every bit of V2 and every bit of V4 we are XORing. You get 1111. What is 1111? 1111 is similar to V3, right? Yes. Next, V4 and V3. We are adding V4 and V3. What do we get when we add V4 and V3? We get 1010. Bit by bit XOR operation. So we get 1010. So where is 1010? 1010 is same as V2. So even if we add any of these components, V1 plus V2 or V2 plus V4, V3 plus V1 or anything, you get a new sequence. That new sequence already exists in the given set of codes, right? So C is linear. Addition of two codes giving a new code word. That new code word can be mapped to the original set of code words. That is called linear. Okay, so we will see in the next slide. Okay, maybe one more and enter. Okay. Oh yeah. Okay. So here the next step is to check for cyclic property. We checked the linear property, cyclic property. What is cyclic property? You just need to make it as a cycle. Cycle means you just keep shifting. For example, we had V1, right? V1 is what? All zeros. We will shift it by 1 and we will call it as V1 prime. So when you shift it, what happens? V1 prime. Again, it is 0, 0, 0, 0. Because if you have 0, 0, 0, 0, you shift it in any way, it is 0, 0, 0, 0. Okay, now V2 prime is equal to what? It is actually the shifted version of V2. V2 is shifted by one position. That becomes 0, 1, 0, 1. 0, 1, 0, 1 is what? V4. Okay, now V3 prime, V3 dash is what? It's one bit shifted version of V3. V3 is all ones. So even if you shift to the right, you get ones itself. So that is same as V3. Now V4 prime, what is V4 prime? It is a one bit shifted version of V4. Okay. So when you shift it, you get 1010. This 1010 what? It is same as V2. So even if we shift it, yes, here, cyclic shift to a code word in C produces another code word. So it's a linear cyclic code. We shifted it in a cyclic manner. That means we shifted to the right, and last bit becomes first bit becomes second bit, and so on. Circular shift. Then we got some new sequences: v1 dash, v2 dash, v3 dash, and v4 dash. They are actually same as v1, v4, v3, and v2. Somewhere they can be found in the original set of code words. So even if we shift it, then it's the new code words are again the original code words itself. So it exhibits linear property as well as cyclic property. So cyclic linear codes. Okay, so this is how we verify a given code is cyclic as well as linear. So in the next slide, we will see some, yes, some new terms here in this slide. So I have mentioned here is as a generator polynomial and cyclic codes. So we use something called as generator polynomial. This is very, very important actually. Okay, so how do we do that? Because to verify these cyclic codes, we need to use something called as generator polynomial. How to choose the generator polynomial? That we will see here in the very beginning part of this slide. See, to generate a n comma k cyclic code, the generator polynomial gx must satisfy two conditions or two properties. So what is the meaning to generate n comma k cyclic code? You have k bits of data. You want to convert or encode it into n bits. Okay. Now to do that, we use a generator polynomial. So what is the property the generator polynomial should exhibit? There are two properties it should exhibit. First property, degree of generator polynomial is n minus k. Degree in the sense what? Power. Because generator polynomial is expressed as a polynomial, maybe x power 5, x power 4, x power 3, and so on. So the highest power of this generator polynomial is n minus k. Okay, n is a number, k is also a number. So n minus k is a number, right? So you get maybe 7 minus 4 is 3. So its highest power should be 3. So x cube and like that. We have an example later on. Okay, the second property is generator polynomial is a factor of x power n plus 1. So I said n and k are some numbers, maybe 6, 3 or 7, 4 and so on, right? So n is a number, maybe x power 6 plus 1. So the second property says generator polynomial is a factor of x power 6 plus 1 if n is equal to 6. So what is a factor? The factor is a key word here. So factor means when you divide, it should be a multiple. Factor means it's a multiple of x power n plus 1. For example, a simple example I would like to give here. 2 is a factor of 14. 3 is a factor of 12. 7 is a factor of 35. Right? Yeah, you got it. Right? It should be divisible that way. Okay. Next, once the generator polynomial is constructed, it generates n comma k cyclic codes, C, in which the code polynomial v of x of a message vector. Okay, this is just a representation. How do we do that? First, we need to have a generator polynomial. So generator polynomial, when we choose the generator polynomial, it should exhibit those two properties. You have to choose the generator polynomial so that they exhibit those two properties. And then once the generator polynomial is constructed, it generates a cyclic code, what we want, in which the code polynomial Vx, the contents of the cyclic code will be V of x is equal to d of x multiplied by g of x. So the code what we generate, V of x, is nothing but the multiplication of d of x. What is d of x? D of x is a data bits. How many data bits we have? K number of data bits. They are varying from 0 to k minus 1. D0, D1, D2, dk minus 1. Okay, that is in general represented as d of x multiplied by g of x. What is g of x? G of x is the generator polynomial that we have just generated in the above step. So ultimately, here we have overall idea. The given question may be sometimes construct a cyclic code of 6, 3. In that case, what we have to do? How to solve this problem? How to construct a cyclic code? First, we need to have a generator polynomial. How to choose the generator polynomial? We have to take care of these two properties. We have to choose the generator polynomial. It should be n minus k order, and it should be a factor of x power n plus 1 that we have to take care. Okay, then we will get a generator polynomial. After that, we just need to multiply data. Data will be given. From that, we have to multiply data and generator polynomial. We will get the v of x. V of x is nothing but the cyclic code that we want. Okay, so this is the general theory. We will see in the next slide. Yeah, this is what I mentioned. Data is what? D0, D1, D2, and so on. Dk minus 1. Totally we have k bits. And in the polynomial form, we write it as D0 plus D1x, D2, x square, and so on. Anyway, these D0, D1 are binary, 0 or 1. Their coefficients values are 0 or 1. Okay, in the next slide, we have an example right here. Example. For a 7, 4 cyclic code, find the following. What you have to find? Possible generator polynomial. Second, the code word for the message sequence 1111, 1010, 1110, 01010. So the question here, you can relate it to the previous slides, what we discussed, the general idea. N comma k cyclic code word you need to generate, then how to do, right? So here n is given as a 7, k is given as 4. First you need to have a generator polynomial. So how to do that? You need to take care about the properties. When you generate some generator polynomial, when you assume some generator polynomial, you need to take care whether it follows those two properties or not. Okay, in the solution, I have mentioned that n is equal to 7, k is equal to 4. That is given in the data. And then assume, let g of x as something that is x power 3 plus x power 2 plus 1. It is just an assumption, random assumption. But when you solve more examples, you will get that idea how to choose that. Okay, whatever you have assumed, it should exhibit the properties. Now we will see whether it exhibits that property or not. Now divide x power 7 plus 1 by g of x. We have assumed some g of x. And now we divide x power 7 plus 1 by g of x. Why? Because the second property says whatever generator polynomial you consider, that should be a factor of x power n plus 1. That's why I have written here x power 7 plus 1, right? So we have assumed some generator polynomial randomly as x cube plus x square plus 1. We have to check whether this generator polynomial, is it a factor of x power n plus 1, that is equal to x power 7 plus 1. Is it so? That is the second property we are verifying. So how to verify? When we say it's a factor, how to verify that? When I say 2 is a factor of 14, how do you say that? We have to divide, right? We divide 2 and 14 and it divides. I say 3 is a factor of 12. That means you have to divide 12 by 3 and it divides, right? Then it's a factor. Similarly, you have to divide x power 7 plus 1 by x cube plus x square plus 1. And you have to check whether it divides or not. So division operation we have learned earlier. I asked you to take your pen and paper and solve it, how to divide, right? So that thing you have to apply here. In the next slide, we will see the solution directly. Yes. So x power 7 plus 1 divided by x cube plus x square plus 1. So again, I cannot go through the steps here. So maybe you can try to solve it by yourself. Or if you have any questions, you can write me as an email. I will answer it. Or maybe if it is still not clear, then in the next lecture, I will explain this in steps. So okay, anyway, when you divide, you get a reminder here as a 0. That means it completely divides. So x cube plus x square plus 1 is a factor of x power 7 plus 1. So that gives us the strength that we have proved the second property. Second property is solved, I mean verified, by choosing a generator polynomial. Okay. So I think I should go to the next slide because I cannot explain anything here. Okay. So basically that was the division operation, what we learned earlier. Okay, here the remainder is 0 in the division operation. So that proves the second property. Now, do we need to check the first property? Yes, of course. So what is the first property? It says generator polynomial must be a power of n minus k. So n minus k is what here? 7 minus 4 is 3, right? So x is equal to 3 in g of x. That means the highest power is 3, right? In a g of x, what we have chosen, its highest power is 3x cube. Yeah, that is also verified here. We randomly chose something, but it exhibits that property n minus k, that is 7 minus 4 is 3. 3 is the power of the generator polynomial, that is x cube. Generator polynomial starts at x cube plus x square plus 1. So both the properties it satisfies, so no worry. We can directly use g of x. What we have assumed, it's a valid generator polynomial. So since we know the properties, by seeing the question itself, you will get some idea. It need not be x power 3 plus x square plus 1. It can be something like x cube plus x plus 1. Why not? Maybe that's also okay. I have given here. Check. Can g of x be x cube plus x plus 1? Will it work? I don't know. So how to check? The first property, of course, it exhibits, right? Because it starts with x power 3. N is 7, k is 3. Sorry, k is 4. So n minus k is 3. So generator polynomial should start with 3. That means x3, x power 3. Yes, property 1 is okay. Property 2, this generator polynomial should be a factor of x power 7 plus 1. That means when you divide x power 7 plus 1 by this generator polynomial, g of x is equal to x cube plus x plus 1. You should get 0, remainder as 0. Will it work? I don't know. Maybe you need to check. So this is how we verify. If you get 0, of course, this is a valid. Otherwise, you need to just change some powers and check until you get a generator polynomial that is valid. That means it should exhibit both the properties. So that's a challenging part here in this question. Okay, then we will move on to the next slide. Okay, so the first step is over. We have chosen the generator polynomial. Yes, it's fine. Then we need to check the data, right? Data is given here. The first data is 1 1 1 1. When you represent it as a polynomial, that is d of x is what? 1 plus 1 multiplied by x plus 1 multiplied by x square plus 1 multiplied by x cube. I have given different colors here to indicate what's the direction of x power increasing. The first bit is red color, right? That means x power 0. Second bit is green color, right? Because 1 multiplied by x. Third bit is again some other red, brown color. So that 1 multiplied by x square. The fourth one is black. 1 multiplied by x cube. In that direction it is increasing. Okay. So that is how we represent d of x. Data is given in the question. We represent it as d of x. And then we want to get the first code word v of x. V of x is what? Just multiply d of x with the g of x. G of x already we found. D of x we have just obtained. You just multiply those two terms, d of x multiplied by g of x. Multiplication we have seen how to do, right? So when you multiply those, you get 1 plus x cube plus x power 5 plus x power 6. What is the meaning of this? First bit is 1. There is no x here in the result, no x square. So 0, 0. X cube is there. So you have a 1. X power, no x power. So 0. X power 5, yes, there is 1. X power 6, yes, there is 1. So v is equal to 1, 0, 0, 1, 0, 1, 1. What's the meaning? The first bit is 1 because in the result after multiplication, we have a 1. The next bit is 0 because there is no x. The next bit is also 0 because there is no x square. Yes, she's pointing rightly. And next bit is 1 because there is x cube. The next bit is 0 because there is no x power 4. The last two bits are 1 1 because in the result we have x power 5 and x power 6. Just we are mapping. Okay. Similarly, for other data you can try it. I think it is time, even though we started a little late, but I should stop it here at this point. So similarly, you check for other data. There are other 3 data sequences. We do the same operation. So you get different V's here. So that is what we need. I have shown for one data here. Similarly, you try for the second, third, and fourth data sequences. So yeah, it's fine. Maybe the students will do it by themselves. So thank you very much for today's attending today's lecture. And this is the end of today's lecture.